Hi everyone, I am Dr. Esan and today I am going to discuss about crystals, atoms to rocks, to the highest scale from the lowest scale, from the microscopic world of atoms to crystals and how the crystals make up of the minerals and the minerals that make all the rocks, be it sedimentary or igneous or metamorphic. And then we will also see some fun facts regarding the tectonics, the plate tectonics, and the magnetism of our planet, regarding how the planet behaves. So, as you can see in this particular example, all these lattices or the cells are with a very organized geometry to form crystals or minerals. In this example, as you can see, a beautiful olivine crystal, and the dimension is also given, right? So this one cell, when it becomes an n number of cells, is when we get this assembly of crystals forming a rock. So in this second example, this is another crystal or element that comes together and forms a mineral called forsterite. So you can see the cell structure of forsterite, two rectangular faces and two other faces shown in few different angles on this beautiful animation. So this arrangement of the tetrahedra is actually different from olivine, or in these examples, these are just examples of many different type of crystals and that are made up of different cells and then ultimately make up minerals, and then the whole organization makes up a rock, as you can see in this beautiful animated 3D model. And examples that we see in nature are many, but the most fascinating thing about this is how beautifully these are organized, from a chemical perspective. The bonds that you see, the structures that are made only because of their different orientations or different ways of bonding chemically, makes different set of minerals and different set of mineralogy, and these different type of mineralogy are applied in different type of crystals forming different type of minerals, and when we join all the crystals together, we form a particular rock. So try to appreciate, from crystals to minerals to rocks, we come to see how the plates are distributed. It's a very fascinating world of what we are living on. So all the everything that is on this planet are on different continents, right? And you can see these continents are made up of different fragments of plates, and in this particular animation we are showing you how the plates move across the surface of the planet. So these motions are actually along the circles, and it has particular axis we call as Euler pole, which actually is the intersection of this axis that is shown here, and you can see north and south. So this is the Euler axis, and the plate motion is described by the rotation about this particular axis. So the axis of the magnetic north and south and the axis of the plates are different, and this is how we get all the motions of these plates. Although we can't feel that, but with sophisticated technologies, sophisticated instrumentations, we actually can see how far or how much these plates actually move in time and space. This is exactly why we sometimes feel earthquakes of different magnitude. So when these plates collide with other plates, then we get different type of motions, and sometimes we get energy that are locked up uh, in different type of motions, and this is how we get natural phenomena like earth. But in this example, I'm just showing you this single plate on this rotation around the sphere's axis. This actually describes the movement of the plate on the sphere surface, which is our planet. Okay, so on the previous example, I was showing a single plate, how the plate moves across the planet's surface. Now, let's imagine the different fragments of the plates and the motion of these plates at different sections, like convergent across the or along the subduction zones you can see. And so this triangulation line are actually subduction zones, and you see the arrows going away from each other are the divergent zones, and then the transverse motion at the transform fault locations. So these three major locations or three major areas form three major type of forces when the plates collide across the Euler axis of these plates. So this is very important because, as I said, the movement or the motion of these plates are crucial in the sustainability of this interplanet. It's not only always regarding the disasters like earthquakes. The motion of the plate is so important, so crucial, although we don't feel it or we don't really sense it unless we have a very sophisticated tool to just go through or to analyze this motion. We actually understand or see the very nature of these plates and how these plates move across different axes along the Euler axis, which I believe you now know. So the velocities of these plates are varying. Sometimes it is fast, sometimes the plate movement might be slow. But don't get me wrong, these velocities are not like the velocity of your average car, which is maybe 50-60 km per hour. These plate velocities are pretty minute, pretty small. We don't really feel that. For example, plates that are converging along the subduction zone of close to Bengal Basin have motions as low as 8 to 10 millimeter per year. So you can see how minute these motions are, but this small motion or motions in plates can make or can play bigger roles when it comes to organizing the consequence of the plate movements or the plate movements. So these are essential mechanics of our beautiful planet. So it's described by rotation, as you can understand, and the plate motions are along the Euler axis, and the velocities will be varying across different plate boundaries, and it's pretty low. We don't really feel that. When do we feel that? Is when we see this in the form of earthquakes. So this is our beautiful planet, and this is the magnetic field that we have, and this is the pole. So for simplicity, this field is assimilated on the surface to a magnetic pole. So these are the magnetic fields across the planet, a representation of the field lines, as you can see, which cannot be seen but can be felt. So volcanic rocks, for example in here in Cape Verde, normally contains ferromagnetic minerals such as magnetite, whose magnetization is in the direction of the ambient field. You can see the direction of the field. That's the direction. So during the cooling of these rocks, the orientation of the ambient field is memorized in these minerals. Isn't it fascinating? Not only human beings memorize, the rocks, the crystals also memorize the direction. So the magnetization orientation of a 240 million year sample differs from the orientation of the current magnetic field. So it has a really serious consequence or an understanding that the fields, the poles have probably been shifting positions along the history of the geohistory of our beautiful planet. So here is another sample of 240 million year old sample located in South America. So if we draw this imaginary line, the orientation of the magnetization will differ from the orientation of the current magnetic field. To explain this orientation, a virtual geomagnetic dipole is again determined. You can see that from the direction. So for this sample, a distinction is made between the two virtual geomagnetic dipoles. At every moment, this geomagnetic dipole is going to be unique for the sustainability of the magnetic field of planet Earth. Only a drift between, for example, Africa and South America allows to find the unique dipole that actually existed 240 million years ago. So you can see what happened millions of years ago can be traced back because of the memorization, quality of the crystals, the ferromagnetic crystals, and this is how we can trace back how the plates have been moved and how the poles are shifting. Isn't it, fascinating? What could be more fascinating than this? So with that in mind, thank you very much to all of you, and we'll be seeing each other, in the next video. So until then, best wishes.